What's up, guys? We're doing 3.3 video today. It may be split up into two videos. We'll see how it goes. Zeros of polynomials. I'll go ahead and say this at the beginning. It's a lot of theorems, definitions, stuff like that. Hang in there. They're kind of confusing at the beginning, but the practical application is fairly simple. Alright, so let's just jump into it and see how we do. This is section 3.3. Alright, so we're going to start off with a definition that we've already talked about, but we'll review it just in case. The zeros of a polynomial f of x are the solutions of the equation f of x equals 0. So remember, we talked about it before. Zeros are just the x-intercepts that make the function 0. So zeros are x-intercepts. Okay. Next up, we have the fundamental theorem of algebra. Alright, it states this is also in your book. If a polynomial f of x has a positive degree and complex coefficients, then f of x has at least one complex 0. Alright, so we'll talk about this a little bit more in detail when we start throwing examples up there, but just take a minute to review that, think it over, think about what it's saying. Let me put this up here. Recall a complex number is a number with the form a plus bi, right? Where a and b are real numbers, but together we make an imaginary number. Recognize every number technically is a complex number. So, for example, certainly 7 plus 2i is a complex number. Recognize also that the number 7 is a complex number, right? With just 0i. So every number can be considered a complex number with 0 equal to the b term. All right, so that's what this fundamental theorem of algebra is talking about. A polynomial f(x) has a positive degree. So a degree and complex coefficients. So remember your coefficients. You know, ax squared plus bx plus c. These are your coefficients, your a, your c, your b, your your c. So it's saying if there's complex coefficients and a positive degree, then there's at least one complex 0. And we'll see examples of that moving forward. Alright, here's another theorem. It's the complete factorization theorem. Or polynomials. It's a big long title, but it doesn't really tell us anything we haven't seen already. If f of x is a polynomial with degree n greater than 0, so again, just a positive degree, then there exists n complex numbers we'll call them C1 through Cn, such that f of x equals a, which is a constant term, times x minus C1 times x minus C2 all the way through x minus Cn. Alright? where a is our leading coefficient, and each c sub k is a 0 of f of x. So we've been dealing with this, we've been seeing this for a week or so now, but now we're just dealing with the possibility of complex numbers. So it's nothing too crazy. Let me give you an example of what we're looking at. So let's say f of x equals 3x squared minus 12 plus 6i x plus 24i. Well, what that can be factored with a leading term of 3, and the factor is x minus 4, x minus 2i. So here's our a from here, and then our zeros are simply 4 and 2i. Okay, so this is just kind of a practical application with complex zeros. All right, so again, it sounds tricky, it sounds a little tough, but in practical application, it's not really anything we haven't seen already. All right, we've got another theorem to cover here, and then we'll keep moving on. So still relating to complex zeros, polynomial of degree n greater than 0 has at most n different complex zeros. So in other words, going back to this example, polynomial of degree n greater than 0 has at most n different complex. So this was degree 2 here, degree 1, so a degree 2 here, so we get 2 zeros. Polynomial of degree n greater than 0 has at most n different complex zeros. So it's something we've been dealing with for the last week or so. All right, let's look at an example. Find a polynomial f of x in factored form that has degree 3 it has zeros 2, -1, and 3, and it satisfies f of 1 is equal to 5. So we want to find f of x such that it meets all these criteria. A degree equal to 3, zeros of this, and it satisfies f of 1 equal to 5. So let's see what that's going to look like. And we'll use it. Basically, this problem is going to use all the theorems that we put on the board up to this point. All right. So recall in last, I think it was 3.2, the factor theorem. Well, the factor theorem, we know that x minus 2, x plus 1, and x minus 3 are factors. Factors of f of x. We're told that these are zeros, right? And the factor theorem says, well, if these are zeros, then the remainder has to be 0, and therefore these are factors. So we can go ahead and say f of x, this is what we know up to this point, equals a times x minus 2, x plus 1, x minus 3. So we need to figure out what a is with the rest of the information. Well, we know it has degree 3, we're good with that. The other part that we know is f of 1 equals 5. So that's how we're going to solve for our a. We're going to say 5 equals a, times 1 minus 2, 1 plus 1, and 1 minus 3. Or 5 equals, I think it comes out to 4a, which implies that a equals 5/4. So now we can say that f of x must equal 5/4 times x minus 2 times x plus 1 times x minus 3. And you can multiply all that out, and I'll give you the final answer here. We get 5/4 x cubed minus 5x squared plus 5/4 x plus 15 halves. These two things are saying the same thing. So given this information, the zeros, the degree, and one piece of information as far as an x-intercept, we can come out to what the polynomial actually is. Alright, not too bad there.
11 minutes.
Let me put a stop to the video here, and I'll pick it up with another definition on the next video. Alright?